Okay, so this week's lab is on the RC circuits lab. So you may have noticed in the video section that there were a couple of videos prior to this one, which are actually from the lecture class. So if you haven't already watched the introduction to RC circuits from the lectures, from the lecture class, then you should definitely watch those videos to sort of introduce you as to what an RC circuit is, what is a charging circuit, what does a discharging circuit look like, charge is a function of time, current is a function of time, and what those functions actually look like, and what the definition of the time constant is. So what we're going to be doing in this lab is I'm actually going to show you how we can actually experimentally determine. First of all, we're going to use the oscilloscope to plot these curves on the oscilloscope screen, plotting charge and current as functions of time. And then basically, of course, we're going to be using voltages as stand-in, but you'll see how we do that. But anyway, and then we will be measuring time constants, spending some time on that. Anyway, so let me get into the connection between the theory that you would have learned about RC circuits and what we're actually going to be doing in the lab here. So first of all, what we have is we have a circuit. So let me just remind you just briefly what the RC circuit looks like. So we have a resistor and then we have a capacitor here. And so the idea is we have some sort of switch which we close at t equals 0. And then what happens is that the power supply voltage initially ends up over the resistor. The capacitor is initially uncharged. But then what happens is over time there's a current in the circuit. The current, by the way, is limited by the resistance. So the current doesn't allow charge to build up right away, but it has to do so slowly over time. And so if you were to plot Q as a function of t, then it looks something like this. And you can relate the maximum charge. That's just basically the capacitance multiplied by whatever the voltage of the battery is. So I'll just write it this way. That's sort of the maximum charge. And you get this exponential curve here. And then if you were to plot current as a function of time, the current actually starts at the battery voltage over R. That's the current when the voltage is across the battery, and then this thing decays exponentially. And there are exponential functions there, and you can define the time constant, and so on. And so basically what we would like to do is we would like to plot this. So this is for the charging curve, and then for the discharging curve, we just take the power supply out, effectively setting it to 0. This time the capacitor has an initial charge, and then the idea is that if I were to plot Q versus T, now I would end up with some kind of exponential decay here. Like this, there would be some initial charge. It would decay to 0 exponentially. The current would also decay exponentially from some initial value, and that would decay also to 0. Like this. Okay? And then there's a time constant which governs all of this, which can be written in terms of RC. So that's basically a summary of what you would have learned there. Now, if we try to actually set this up, right, if we actually try to set up this circuit and then try to actually measure these curves here. So first of all, the easiest way to measure anything as a function of time is to use the oscilloscope. But remember, the oscilloscope doesn't have the ability directly to measure charge on a capacitor plate or current running through a circuit, but it can measure voltages. And so, of course, what we do is we translate this into voltages. So instead of measuring charge as a function of time, what you're actually going to measure is the capacitor voltage as a function of time, because that's given by Q divided by C. And then instead of measuring current, you measure the voltage across the resistor, because that's given by R times I. Right? And so basically the VC versus T graph and the VR versus T graph should look like the Q versus T and the I versus T from the theoretical standpoint. And the same thing happens here. So we do VC and VR as well. So what we can do is we can hook up the oscilloscope here. And so the first thought might be, okay, well, let's just literally hook up the circuit this way. We'll have a DC power supply here ready to go. We hook up a switch here, which we're going to press down at time t equals 0. We've got a resistor. We've got a capacitor. The capacitances that we have in the lab room, the ones that we're going to be using for this lab, are 0.01 microfarads, sort of nominal value. So that's 10 to the minus 8 farads. The resistance is going to be on the order of about 10 to the 4 ohms. We have a variable resistor that we will hook up. If you put this together, then tau should be on the order of 10 to the minus 4 seconds when you get done. Now, this is important because this happens very quickly, right? This time constant is extremely short. So if I tried to do this experiment literally the way I've drawn it here, what you'll discover is that it's over before you even get to blink, right? You're going to get this charging curve, and then all of a sudden the charge is going to be at some constant value, and that's it. And then the current's going to, the resistor voltage is going to like start big and then flip to 0, and then it's gone before you get a chance to see it. And then the oscilloscope screen from that point on is just going to look like horizontal lines, and you're not going to see anything. The same thing if you started with the capacitor already charged, and then you put a switch here, took the power supply out, replaced it with a wire, and then discharged the capacitor and did the same kind of hookup. Again, this would all be over before you had a chance to even see it. So what we're going to do instead is we're actually going to hook up a circuit that allows us to alternate between these two, back and forth. And the way to do that is to hook up a function generator that is generating a square wave. So this is what you're actually, this is what we actually hook up here. So we use a function generator. The function generator generates a square wave. So let me just draw the voltage that we are going to get from the function generator as a function of time. So it's going to initially spend some time at some voltage that's away from 0. So that means then, in this case, the circuit's going to act like the charging capacitor. And so the capacitor should charge, and the charge should look something like this. And then what's going to happen is, so this is during the first half cycle. And then during the second half cycle, this thing is going to drop to 0. So I have to set up the signal generator this way. This is going to drop to 0. And then now it's going to act like this circuit, and we're going to end up discharging. And now the charge as a function of time is going to look like this, and so on. But the nice thing that happens is, so I've got the oscilloscope screen, it's going to show one of these, but the fact is that it keeps doing this over and over again, and the oscilloscope just keeps displaying the same display over and over again. And so what ends up happening is we get the charging and discharging curves. Basically ends up being a stable image on the screen. So if we plot VR as a function of time, we should end up with these two graphs here. So indeed, you're going to end up with something that looks like this. And then actually, the discharging case, it's going to be negative. Think about why that would be the case here. Right? When I talked about the current here, I kind of assumed that a direction for the current, which was this way, because after all, this is the way it would move when it was discharging. But the way we hook up the oscilloscope, this is actually going to show up as a negative voltage. So that's why that's actually flipped upside down like that. And then the VC, that's just going to look like the charge as a function of time. So you're going to get something that's charging, and then it's going to go from here, and it's going to discharge. And so you're going to end up with graphs that look like this. And so in fact, part A, looks like I didn't draw this quite right, but you should do this at equal times. You should basically get charging and discharging curves here. Okay? And so that's really the point of part A here. I do want to talk a little bit about the time constant, because one of the things you're going to be doing in parts B and C. So actually, let's talk a little bit about the time constant, just to summarize it here. So we'll just look at the discharging curve for the capacitor. Right? So remember how this works, right? There's a certain amount of charge on the capacitor plates. After a certain amount of time, this charge is going to drop by a factor of 1 over E. And it turns out that this is equal to the time constant. And then if you were to weight another time constant, then this would drop by a second factor of e. And so on. So this is actually a characteristic of exponential curves, is that if you wait a certain amount of time, the signal will drop by a factor of e. If you wait the same amount of time more, then it'll drop by another factor of e. And if you wait the same amount of time after that, it'll drop by another factor of e. So it always drops by the same factor in the same amount of time. And in fact, it turns out there's really nothing special about e. It's easier to express the function and the time when you're using the factor of e, which is, by the way, is the natural base. It's not the electron charge, so don't put in 1.6 times 10 to the minus 19 here. This is the 2.1 or 718 or something like that, that value. There's nothing actually magical about e, and in fact, people, in reference to exponential curves, often talk about half-lives. And so one of the exercises I'm going to actually have you do is I'm going to actually have you, so let me actually, this is the start here for the decay curve for the, actually it's here, for the capacitor, is I'm going to actually have you take these curves and I'm going to have you demonstrate what is called the half-life property. So this is kind of a starting voltage here. So think of this as V0, and then this will be V0 over 2, and there's a certain amount of time, which is the half-life. And then there's going to be another certain amount of time to go to V0 over 4. And if I had drawn this accurately, it should be the same half-life. And then you can go out to V0 over 8. And I'm going to actually have you do this after you've drawn this diagram here. Your assignment for part B is to actually show that this decaying curve here obeys the half-life property. And there's also a similar half-life property for the resistor, for both the charging and for the discharging, right? Again, it should be the same amount. I didn't draw this very well, so it might not look like the same. But if you do a careful job of drawing the actual curves that you see on the oscilloscope screen, you should be able to get a pretty good match here. These should be the same time interval. This is usually taken to be evidence that you are looking at an exponential curve and not some other function. I'm going to actually leave it to you to figure out what to do with the charging curve. This one's different because the target value is not 0. So I'm going to let you try to figure out how to demonstrate the half-life property on the VC curve here. But anyway, so what we're going to be doing in this lab is, so part A is basically about drawing these diagrams here, and I'll show you, the demo of how that was done, and then you'll be able to use the oscilloscope screen images to do that. Then part B is about demonstrating this half-life property, and then part C, that's going to be about actually measuring the time constant. And so what's going to happen with part C is actually, so we've actually got two capacitors, C1 and C2. So we're going to be doing most of our work with C1 here. But when we go to measure the time constants, we're going to actually measure the time constants for C1, for C2, and for C12, which is basically the parallel combination of 1 and 2. So again, what you're going to do is you're going to plot this. Right, so we've got this. So what we're going to do is we're going to look specifically at the capacitor voltage. So remember how this is done, by the way, right? Let me actually just finish this, right? So this is channel 1 here, channel 2 here, usual red, black, right? In fact, part A of this lab is going to be done exactly the same way as part D of the diode lab was done. I mean, it's basically the same setup. The only difference is you have a capacitor here instead of a diode. But it's the same setup, right? This is going to be channel 1. This is channel, well, let's see. This would be channel 2, and then this is channel 1 minus 2. Okay? And so that's basically how that works. But anyway, what we're going to be doing for part C is we're going to use the same circuit with the same oscilloscope connections, but we're going to change the oscilloscope screen so what you're going to see on the screen is actually going to look more like this. So we're going to just basically blow this thing up. And you're going to have some initial voltage. There's going to be a 0 line here. What you're going to see on the screen is going to, let me get this right, it's going to look something like this. Now, there's an implication that this thing will eventually decay to 0, but you won't see this on the screen. You'll just see this part of the screen here. Now, what you can do is you can play with the time base here. So you can initially increase the time base so that you are seeing more of this curve to verify that this is hitting the time axis here. And then you can actually set it so that it hits the bottom axis on the screen. But then what you do is you expand the time interval by decreasing the time per division. And what happens is this thing does not actually reach 0 by the time it reaches the end of the screen, but you know that it will eventually reach 0 at a later time. And you'll be able to use this curve to actually measure the time constant. And so what I'm going to have you do is plot this VC versus T for the first capacitor. I'm going to give you the oscilloscope screen so you can do that. You'll just plot that on graph paper, and then you will actually do the following construction. So, right, you figure out what V0 is, just based on the axis here, and then you divide that by E. And again, here's where it's important to know that E is not 1.6 times 10 to the minus 19, right? Again, it's 2.718 or whatever it is. But you divide that by E, and then the idea is if I were to map this over, then this should be the time constant here. And so this gives us a way to actually measure the time constant. I'm then going to actually show you how to get this with cursors. I'm going to actually take you through the process of how that's measured with cursors. Unfortunately, since you don't have an opportunity to do this lab yourself, you're not going to get a chance to do this with cursors. This is actually one of my favorite exam questions. I usually give students this problem, you know, like I give them an RC circuit to construct, and then they have to actually use the oscilloscope and use the cursors method. It's actually pretty quick once you get used to doing it, but to measure the time constant. Once you have the time constant, by the way, you should be able to calculate the capacitance, right? Because the capacitance is just simply going to be the time constant divided by the resistance. The only wrinkle here is that you want to use the total resistance. So the total resistance is given by the resistance of the resistor, and there's also the resistance of the function generator itself. When I first got here, the function generators we were using had an internal resistance of 600 ohms, and so it was really important to add this term. Actually, we're using different function generators now. So the resistance of the function generator now is 50 ohms. So if you read this in the lab textbook, you may notice that they say that the function generator resistance is 600 ohms. But the function generators that I used when I took the data, that's 50 ohms. So this is almost negligible, but it's still at least conceptually important that you understand that you're supposed to add that. So I want to see you add that in. But anyway, you'll be able to calculate the capacitance based on that. And then what I'll do is I'll actually give you the cursor's measurements for C1, C2, and then the parallel combination of C1 and C2. So you're actually going to be dealing with these three capacitor sequences. Let's see, this is going to be a parallel combination here, C1 and C2. Right, so you're going to be working with these three, and you're going to get three time constants. One of the advantages of the cursor method is because it's so fast, you don't end up having to spend a whole lot of time doing it, and it actually makes sense to take the time to measure the tau 1 and tau 2 separately. Even though the capacitors are both supposedly 0.01 microfarad capacitors, they will differ slightly, and you will get slightly different time constants. In fact, that's what I got, and that's usually what students get when they do the measurements themselves. And then tau 1, 2, this is basically the time constant associated with the parallel combination here. But anyway, you'll be able to measure C1, C2, and C12, and there's actually it's actually a percent difference test at the end, where I actually have you compare C12 with a value that you would expect for C12 based on C1 and C2, kind of mirroring what we did in the DC circuits lab when we were doing equivalent resistances. So you're going to do something similar with equivalent capacitances. Normally, I tell the students that you should be within 5%. I haven't actually fully analyzed the data yet, but based on what I've seen, I believe it's going to actually be a lot closer than that. Usually when I get the students to do the lab themselves, the biggest source of error is that they don't get this zero aligned properly. That can be a very big source of error. But since I actually did the data, I, of course, know how important that is to do it right, and I took the time to do it right. And I actually showed you, so I'm going to actually show you in the next videos how I actually took this data and how this data is taken. And so again, yeah, what we're going to do is we're going to go through the Part A data taking and then the Part C data taking, and then I'm going to go through the lab, so as we've done with other labs. I'll actually go through the exercises at the end to show you what you're going to be doing in the analysis. Anyway, so that's in the next videos.